is equal to, now I want this to be kc times the derivative dE dt. Why do I want that? Well, remember we said that the integral controller is sluggish because it doesn't get going until the integral is built up. The proportional controller is not as sluggish as the integral controller, but let's say things are going fine and all of a sudden there's a problem. So let's say things are going swell. So here's my disturbance. We're having entertainment now versus me. So let's say things are going fine. The disturbance is 0 at t is equal to 0. And then all of a sudden, things start to go haywire. Well, there was a change in slope and things start to go haywire. The proportional controller won't do much here because the disturbance hasn't gotten very big yet. The integral controller won't be doing diddly squat because the integral hasn't gotten anywhere. The proportional controller really won't start doing something until this gets pretty big. So now the P is going to kick in. And maybe only later the I will kick in. Because it's only here that there's really a big difference, the error. And over here where the integral has gotten big. So differential control can say, well, here I notice that the derivative changed. Why should I wait until this gets so big? Maybe I can react right here. So I would like something that looks something like this, kc dE dt. But again, I have to make the units work out. So if I want the units to work out, I want this kc to have the units at mv over e. Well, there's an extra time in the denominator, so I need to put a td in the numerator. And now at steady state, mv steady state, well at steady state dE dt was 0, before t equals 0, id. So now I have mv prime is equal to kc td, and what's the Laplace transform of the derivative? No, 1 over s was the integral. What is the Laplace transform of the derivative? S. So now I have this thing where I have kc std. Don't get any ideas, no STDs here. Times e prime, or e prime of t. So that tells me that g for differential control is equal to mv prime tilde over e prime tilde is kc td s. And now we can go through in the remaining 2 minutes and look what happens if I have an instead of an STI, I have an STD in the numerator. This I don't even have to write out. Instead of the STI, I've got an STD in the numerator. So this remains exactly the same, except KPKC is multiplied by S. KPKC is multiplied by STD. So this just becomes STD here. So what happens when I have an STD there? When I look at the final value theorem, here it is. So the KPTC has an STD here. Well, what happens when I set S is equal to 0 here? When I set S equal to 0 here, this term becomes 0. This term just becomes KD, but I still have the 1 here. So in that case, for the differential control, I just get KD times delta D. In other words, I still get an offset. I still get an offset. And in fact, for the third order problem, I have a cube here and a cube here, but still when I set the S goes to 0, it's the same thing. So this is true whether it's the first order example or the third order example. I still have an offset. So differential control does not help the offset. The offset stays the same as without it. But what it does is it anticipates. It anticipates. The problem with anticipation, as we all know when we're anticipating something, is sometimes you can overreact. So there are two problems with this anticipation. The first problem with the anticipation is sometimes you have some noise, a little bit of high frequency noise. If you have high frequency noise and you're looking at derivatives, the derivative is bopping around and the controller is just going on and off, on and off, on and off. So you really don't want to respond to that high frequency noise, so you might have a filter that if the frequency is too high, you don't react to it. Another thing is, if you're disturbed, if you change the set point, versus time, then you have a step change in the set point. The derivative here is infinite. If your derivative is being infinite, your error all of a sudden went from 0 to infinite to a finite value, the derivative was infinite. You certainly don't want to break the controller, the valves, by all of a sudden trying to do an infinite response. So many times, instead of using the EDT, sometimes they'll change this to DCVDT. So even though the error the SP has changed, and therefore the error has changed, CV has not changed the control variable in a stepwise manner. So sometimes the differential control will work this way. I would strongly suggest, and maybe I'll give you some problems, for you to use Simulink, to hook up Simulink in this manner, and try these two examples with different numbers. The first order and the 3 CSTRs in series, try them. Are there any questions? Okay, I will give you a homework, and let's, I owe you half a class. So on Wednesday, we'll start 45 minutes earlier, because I owe you that half a class. I don't want to wait until the last week. Everyone always hates when you shove in extra material the last week. So this way, you'll have extra fun over Thanksgiving, because you'll have extra material that control.